Buenas tardes. I never did ask you if you guys get dinner before you join the class or you eat during the class. How do you manage your dinner? I think I skip dinner, or I eat after dinner, usually. Or I eat a big lunch. During the class, okay. Yeah, it's an inconvenient time, isn't it? It's fine if you're going somewhere to a classroom, but I guess at home you're going to eat at home. I can't eat because I'm teaching. I do drink, but I don't eat. So the test was done quite well. I just looked at the grades. There was one question very few people got. So I will go over that, but not today. I'll do that tomorrow because I don't want to type it all out. I was going to display it, but I'll do it tomorrow. That was one on probability. And also I want a moment to make sure that I have the right response there. And the other thing to tell you about the test is I had a question on binomial, and some people pointed it out that it's technically not in this material. So I'm just going to drop that from the test. So you don't have to worry about that. Or maybe I can make it. Oh, so which question? You know what? I cannot give you a number because the numbers were scrambled, but it was the question about probabilities. Let's see. It gave you like 6 different probabilities and then asked you to tell me if they are independent or mutually exclusive and those questions. And the one that is on the binomial was about the boxes. So I'm going to dump that one from the options. I'm going to take it out of the test. I don't think you did it that poorly, but it's just not fair to put it in the test. And then I will review the one you had trouble with. It was like this one. That one, and then it says A and B are independent. Etc. Okay, so that one was done quite poorly. Okay, so today what I want to do, unless you have questions, I think someone sent me a question, but I'll look at it tomorrow if that's okay. I'm not so organized to look at that today. All right, so today I want to finish probability and then introduce bin. Does anybody have any outstanding questions? Hello, everyone. I saw that you mostly joined Signal, so I guess I can add you to a group. Right now, I am not too worried about the signal, but if there are problems with your signal, with your internet or your power, do text me, okay? I'll start that group. After class, I'll set that up so we're in Signal together. All right, so where I wanted to go from here was this discussion of conditional probabilities and using Bayes' rule. So using prior probability or conditional probabilities to help us in calculating probabilities of interest. And I hinted at this last class, but let's look at this now. And in the exercises, in the homework, and online, there's quite a few of these. And I think they're important to learn, but I don't focus on this in the final. Like, it's not a huge part of the final, but it's an important thing to learn for understanding how probabilities are used in medicine, particularly. So recall A and B, let A and B be two events with probability A and probability B. Well, how's the sound, by the way? I have a new microphone. Does it sound okay? Do I need to be closer, further? You can hear me? Okay, sounds good. All right, so in general terms, if A and B are not independent, this is how we express the probability of A and B. In general, we would multiply A happening times probability of B if A happened, and that should be the same as probability of B times probability of A given B happened. So those should be the same. I should be able to go either way. And then I reiterate what I said before, that B given A is called the conditional probability. In words, event A will occur 30% of the time, and of those times, event B will occur B given A percent of the time. The of indicates that we should multiply the probability. So this is in general. If they're independent, this reduces to just probability of B. So we can write this in the general form. So this is pretty important. This is quite important to realize that's the real way to calculate the probability of joint events. Okay? That's the actual way to get it in general. But then it reduces down, if they are independent, to just multiplying the probabilities together. That makes possible that I can actually define, if you see algebraically, I can define the conditional probability of B given A as this, right? I just divide this by probability of A. So this is the notion of creating the subset of A. So we're focusing just on the subset. So the given A, the scenario of just looking at A, and the probability of A and B occur given A. So that's true, and also that's true. Now, how many of you have read through this? So it's really important to understand in statistical terms, diagnostic test results. Without getting into the biological realities of diagnostic tests, in statistics, what are we really saying? If 2% of the population has a particular disease, but 3.2% of the population tests positive for the disease, this is telling you that the test for the disease is not a perfect test. It's not perfectly accurate. So look, only 2% actually has the disease, and 3.2% of the population will test positive. So the test is overly sensitive, right? It's picking up more than actually have the disease. And that's information that's really important to convey when you get a test result, that you understand what is the accuracy of the test. So what do we have here? So the main challenge in on working with probabilities is to know what you have. Where is the joint probability? What is the conditional probability? What is, how do I sort that out here? So we're going to go through each one. 2% of the population has a disease, and I'll use the notation that I've given here. So this person actually has a disease, would be D plus. So the probability of D plus positively actually having the disease is 2%. So this is quite a bit of information to know. Like, you'd actually have to know that to be able to do this. So someone has to estimate that number somehow. And then, however, 3.2% of the population tests positive for the disease. So that means that if you're in the population, if you actually test positive, if you have the disease, so the way it's worded here, 3.2% of that population, test positive for the disease. I have to make sure. Okay, so I'm going to introduce testing positive as 0.032. Okay, so that's testing positive. So those are my variables. Testing positive and actually having the disease. Or those are the outcomes, sorry. The outcomes. Events. Now, what else is said here? In other words, a test for the disease is not perfectly accurate. From a population-based study on people with the disease, so this is a large study, it was found that 75% of them tested positive. So this is in the population, so in the subset of people with the disease. It was found that 75% of them tested positive. So this is the with the disease. Okay. So we know this conditional probability as well. So we have these bits of information. Now, say that a patient tests positive. What's the chance they actually have the disease? It's not 100%, right? So what would it be with these kinds of statistics, these kinds of measures? What would the chance that if they test positive, they actually have the disease? So if I go back up here and look, I can rewrite this conditioning on actually testing positive, and I write this as the joint event having the disease and testing positive over, in the subset, in other words, of people who test positive. Everybody okay so far? So I write this and that divided by this. Now I have this, and I don't have this. If I can find this, then I can solve for this. Now where am I going to find this? Well, I have the reverse conditional probability. I have this, and what is this equal to? Well, similarly, I can rewrite that as right? So isn't this the same as that? So aren't the joint probabilities the same? So then all I have to do to find the top is multiply. So this is just like gymnastics, all right? So all I'm doing is using and reusing this relationship or this relationship to get an answer. I need this joint probability. I can get it from the other conditional probability. The inverted probability of this one here. And what I do in the table below is I outline all the different probabilities we're talking about, so you see which ones are complementary to each other. But let's just solve this and then we'll look at that table. So then this would be on the top, I basically get to flip this around and I have all those probabilities. I have the probability of the diseased people testing positive, I have the probability of the disease, and I have the probability of testing positive. So I can calculate the chance that a person who tests positive actually has the disease with those kinds of probabilities. When prevalence is low, you're going to see that the test, finding out the accuracy of the test is going to be shocking. So this is 0.75. This one is 0.02. And this is 0.032. And so what do you get? So whenever you get a diagnostic test, ask these questions about what is the chance that I actually have the disease if I've tested positive? And they should be able to answer you. If it's a newer test, maybe, well, they should be able to answer that question regardless. They should have some sort of estimate. So it's almost 50%, like it's very small. So it's like a toss of a coin. So this is not it's not tremendously meaningful. Okay? So below what I've done here is written to you all of this is the joint distribution. So it could be that you have both a positive test and the disease. Positive test, no disease. Negative test, but the disease, and a negative test and no disease. So it's really important to notice this is what you want. You want this one to be high, right? That if you have the disease, you have a positive test, and you want this one to be high as well. That's the chance of not having the disease and testing negative. So this, I believe, is called specificity. Somebody can correct me. I should probably verify that. And this is sensitivity of the test. I'm just going to double check. No, I did it backwards. See, I do that sometimes. Yeah, it's a true negative rate. So that's sensitivity. Yeah, that's what I want. So the words sensitivity and specificity are used in vernacular language a lot. It's like the way people use parameter. They use it for all sorts of things. It's very specific meaning in statistics. So, oh no, I did do it right, didn't I? Oh, no, I don't even remember what I wrote. So this is specificity here. No, I got it backwards. This is specificity. This is true negative. And this is a true positive. Also known as sensitivity. So you want a high sensitivity and a high specificity of a test. And what was ours? What was the sensitivity of this test? That's the numerator part. It would have been 0.75 times 0.02, right? It's small, slow. No, it's really low. So I do all the calculations here, and I attempt to get some of the calculations into the table just so you see the relationships of the conditional probabilities or the joint probabilities. So what's important to note about this table is I have the joint probabilities in here. I have these marginal probabilities, that's what they're called. And the conditional ones, you write them off the chart. Like you find the conditional ones using the chart, but they're not otherwise seen there in the chart. Yeah, it's a very low sensitivity. I need to make sure. I don't know why I mix this stuff up. I don't do it enough. That's why. It just seems really low. No, I see. It's a conditional. I did it wrong. I can't believe that. So the conditional, okay, I'm going to fix this now. Sorry about if I confused you, but I confused myself too. Okay, so it's not that they're and this and that. It's that do that again. So that these are the joint probabilities, those are the marginal, and the conditional probabilities are off the chart. So sensitivity is actually what we found there. This one is sensitivity. I think I left the terminology off the notes because I didn't want to make it so medical specific, but right now I think it's important. Living in the age of COVID, it's important that we know the difference. So this one is sensitivity is the probability that a person tests positive if they have the disease. So it's exactly that. And specificity is the probability that they test negative if they have the disease. So this is a really good example of the differences, because that was very low, that number we got, that's why it threw me off. That's not sensitivity. So the sensitivity we have is 75%. So a 75% sensitivity results in a 47% chance that a person who tests positive actually has the disease. So sensitivity is like the reverse of what we're interested in. This is really what we're interested in. We want to know if you get a positive test, what's the chance that you actually have a disease? So although 75 seems really, that's kind of good. It's all right, but it's not good enough. It makes the chance that my positive tests even mean something a flip of a coin. All right, so that's sensitivity, and specificity is, let me write down just as a note. I apologize for the confusion. Specificity. So that would be the probability of a negative test not having the disease. So this is a really good example of conditional versus a joint probability. Get your head around that. Okay. So these are called true positives. And this is called true negative. And what's important is that with 75% sensitivity, notice what weighs down the number is this. If the disease prevalence is low, it makes the chance that the test actually tells you have the disease low. Also, if the test, this could also make it low, this variable here, or this probability. If it has a high positive test rate, that can also make the meaningfulness of the test low. All right, so I don't use the terminology in here, but I think it's important to add it in right now. I'm hesitating at what words to write because so a low prevalence of disease makes the test less meaningful. You can read that. Okay? So this is why when they started testing with these PCR tests, they were only testing in hospitals or people in contact with people who might be sick. They weren't using the test en masse because the mass was not necessarily exposed to COVID. And that would generate a low meaningfulness of the results, or low, just because of this number. So the higher the prevalence, when there's, it's an infectious disease and a lot of people have it, that can make the test more meaningful. So the test is not without these considerations. All right. All right, so that leads us to, so that's a practical application, but now that leads us to Bayes' rule. In general, I could do this. If I know about the conditional probability given if I know the conditional probability given B, so I know about if B happened or B didn't happen, so I have information on that, I can use that to sort out the conditional in the reverse, probability of B given A. And you'll get several examples. I gave you a lot of examples to practice that with, and you can see the utility of that. And this is quite powerful. And it all comes from simply understanding that you don't multiply probabilities. Like the fact that probability of A and B is not just multiplying them, right? That's only if they're independent. In general, this is what you get. So this looks like a mess, but if you understand it, all I've done here, just like in this one, I fully expanded. If I was to start this out, I would start with and then the point is, I want to know about B given information on A, but I have information on the reverse. So how can I use that? Well, this one I can write as the conditional of A on B times B happening already. So that's what goes on the top. This is A conditioned on B happening already. And then the bottom can be fully expanded like this. What is this? This is, again, all about B. Notice this is the same as this. So this is B happening times the probability of A given B happen, plus, what is this? B not happening. So the chance of B not happening times the probability of B not happening, given B not happening, that A happens. So this is fully expanding this, knowing everything about A given B, and also A given not B. Now, what is the relationship between these two? That's the last thing you need to know. So this is, as intimidating as it is, all I've done is taken this and expanded it based on knowing information in the reverse and this. What's the relationship between these two? So let's see an example. Oh my goodness. One minute. Okay. Maybe with a word problem. What's the relationship between those? Can you get one from the other? So in this scenario, there's only two states of the world. Either it's rainy or it's not rainy. Well, no comment? Okay, let's do this exercise. Let's use the example. We already know the answer for our example. But let's fully expand. So we already know the answer. We already solved it back here. Right? We did this together. I found the joint probability using my understanding of joint probability, this and that happening, and I solved it simply. Now let's expand it and see what all these probabilities mean with the same example. Is that all right? So I'm going to do this in a more complex way. So what I'm going to do is expand this. This one means, okay, so this is just expanded like with the, as though it's the applying what's called Bayes' rule. So I'm expanding this is originally what it was. I'll just get it from over here. just going to cover that for a moment. All right, so this is where we started. That this is equal to both of them happening conditioned on t happening. So then the top can be rewritten this way as I described. That's what the definition of a joint probability is, that d plus happens and then the probability of t plus given d plus happens. So this is when they're not independent. And the bottom becomes this, because what I'm going to do is the probability of t testing positive and having the disease, or that's why I add the probability of testing positive and not having the disease. So this will cover the gamut This will cover testing positive. Either you test positive and you don't have the disease, or you test positive. Sorry, what did I say? If you test you can test positive and have the disease, or you can test positive and not have the disease. All those together add up to testing positive. So then this, like the numerator, right? It looks exactly the same. You know what? I'll put D first so that you can see that. I'll put it in alphabetical order. That's probably why I did it like that, so you can see they're the same. So having the disease is both. It's either testing positive and having it, or testing negative and having it. So that's what I put on the bottom, and expand each of these. This one expands just like the same as I did on the top, and the other one expands similarly, right? So this is just the definition of the joint probability. So I just use the definition again and again and again. So one thing was to know what this is on the bottom. And the next thing to know is, how do I calculate from what I've been given, how do I get this? Like I know this, I know this. So how do I get this one, first of all? So let's put the numbers that we know already. We know the probability of having the disease was given, right, as 2%. So this is 2%. So what's the chance of not having the disease? Are you guys there? You heard my snip? I thought you didn't hear that. Okay, the question was if the chance of having the disease is 2%, what's the chance of not having the disease? Very good. Okay, so some of you got that. So those are complements. That's why I've written them like this. They're complements. And now this one I know. And what about this one? We know this one too, right? We said that we were given that it was 75%. So what remains is this one. How do we know what that is? That's right, Nivette. Well, we can calculate it. Just like we did originally. We're going to use this property that the conditional probability is just this and that divided by or conditioned on d negative. And we know these numbers. So this one I know. Now where does this come from? So I know the denominator. How do I figure out the numerator? That's the last thing I have to do here. So what I'm going to do is let you guys think about that. We'll pick it up tomorrow, okay? I want you to think about this. That's the last thing we need to do. Review this and realize I gave you enough information before to solve it, so we do get the same answer as before. But if you didn't have that full information, notice all you need to know is, all you need to know is the disease, the probability of the disease, the probability of testing positive with the disease. So you could just look at a subgroup of people with the disease and how many of them test positive. with the test. So you can conduct experiments to estimate these. The only thing that remains that I want to discuss is, where does this come from? I mean, you can also do experiments to get that, but from the information we have, how can we compute that? Do we have enough information to compute that? Okay, so we'll look at that tomorrow. So remember, in the chart are the joint probabilities, and conditionals are computed off the chart using the information in the chart. All right, so what I also wanted to do with you was discuss this exercise together. I asked you to try it. The answer is there, but sometimes it's good to have an illustration. And I guess I need to talk about this too. All right, so let me talk about different kinds of probability distributions, and then we'll look at that exercise, and then we'll get into rules of means and variances, and that will be it. And then we'll come back to it tomorrow, and I'll address the few points I made for review. All right, so what I'm going to do is just do a overview of the sorts of probability distributions that you will see in this class. So it gives you a little bit of like a framework or a foundation of what to expect, that you can focus on these distributions. Now there are, I don't know, hundreds of distributions that are commonly used. Now, there's a few key ones, but there are several that have been developed for use. A normal distribution is one of those that are have been developed and used for estimation purposes, and I'm going to mention some others that we're going to talk about. And in fact, it's going to be quite simple. We're going to keep it simple. I want to speak a little bit about what I call general discrete distributions. This lists the possible outcomes with their probabilities. So this one, I'm going to refer to this variable as the month that our robot arm will break down. So this has been estimated through repeated experimentation, observation, and it looks like the chance that it breaks down by the end of the first month is 5%. The chance that it breaks down within the second month is 25%, and so on. Notice these probabilities by the fourth month none of them last more than 4 months. Okay, so these are the only possible outcomes. And the most likely is up to the third month. right? So the total of these probabilities has to sum to 1, and it does. Now this is discrete because I can list the possible outcomes, and it's a legitimate distribution because the probabilities add to 1. Here is a graph of the distribution. And you just see a spike. Notice there's nothing in between here. It's not like a smooth, I can't smooth out this curve. Okay? It's there's a curve there. You see something there, but it's a discrete distribution. So there's no density to speak of. It's only the spike. So in this case, I could actually talk about x equals 3. So we did something like this, right? When we talked about flipping a coin and the outcomes as a variable. I can say x equals 3 if x comes from this distribution. It actually equals something. Unlike where x is normally distributed, if I wrote x equals 60, you would have to say 0. Or x equals anything is 0. Okay? Okay, continuous distributions have 0 density at a single value. Okay, so then that brings us to the other broader group known as the binomial distributions. Now, we saw binomial distribution already. Here's the example. Now, it looks like a general discrete, but there's actually a pattern here. Not only is it symmetric in this case, but there's a pattern that we're going to learn to exploit in the next unit. How it works is that the binomial phenomenon involves two possible outcomes on repeated trials, and there are up to n trials of where you try to see either one or the other outcome, and then we sum across all of those trials. So this is really the basis for sampling, and sampling theory is the binomial distribution. So this is a graph of, I'm going to tell you where it comes from, and this is a graph representing that distribution. Again, we can't smooth out any curve, there's no density there, but we can see this one appears symmetric with a pattern. So what is a binomial variable? How do you tell if a variable is binomial? X is a binomial variable and has a binomial distribution if it is defined as X is the number of successes out of n independent trials. So X can be 0, 1, 2, up to n. So what you would do if you have a situation where you think, maybe this is a binomial and I can solve this using a simple formula that I learned in my class, or Excel, show you how to use Excel to get your results. Here, it must be the case that each time you repeat a trial or replicate a trial or conduct a trial, that's the word I want. Each time you conduct a trial, you could see either one of two possibilities: a success, the thing you're looking for, or a failure. Okay, so we approach this, it's like an experiment. I approach it, or it's like the best way to call it, to term it, is a trial. So I approach the trial, I want to observe something, and I look to see it. That's called a success. If I don't see it, I call that a failure. The chance of a success is, we name it P, small p, for probability of a success. Now, this probability of success from trial to trial to trial, the chance of seeing what you're looking for remains the same from trial to trial to trial. It needs to be that way for this to be a binomial phenomena. And the number of trials that you repeat must be known. It must be finite. Okay? It must be known. You need to know what it is. So you repeat this how many times? Someone has to say how many times. And it has to be a finite number, not infinite times. So if you have those three criteria met, then you will be able to refer to that variable as a binomial variable. You can express it like this. This means distributed as. And like the normal distribution only needed for the normal distribution, though, the normal random variable, all you needed to know is that it was normal, and you needed to know the two parameters mu and sigma to describe or visualize the distribution. In the case of binomial, all you need are these two, and so we call them parameters for the distribution. We need to know the number of trials and the probability of a success on a trial. So let's see an example of what is a binomial. Find the probability of seeing more than 5 people holding an umbrella on a rainy day if 100 different people are randomly selected and observed having an umbrella or not. The probability of holding an umbrella on a rainy day is known. So this possesses all of the criteria for a random, a binomially distributed random variable. First, there are only two possible outcomes on each trial. Either I observe the umbrella, success, or I fail to observe the umbrella. I know the chance of observing an umbrella. It's 10%. And I know how many times I'm going to look. I'm going to try 100 times. So if you consider that you are a manager in a mall and people are entering the mall on a rainy day with umbrellas. You want to be sure that there's enough either mats on the ground to collect the water, something where the individuals can either wrap their umbrella in plastic or they can shake it out. You want to make sure there's an area for them to enter safely. Water is collected off their umbrella. However it works, you want to make sure that you avoid spills or people falling because of the water on the ground. So you want to see how many people actually have umbrellas, bring them in and drag in that water, and you want to be able to deal with that. So there's my rationale for this exercise. And so after observing people with umbrellas, we seem to find out, or we know, we have this information that 10% of them seem to be holding umbrellas. And so we can estimate if we imagine that there's 100 people at a time in, I don't know, in the morning, that's probably, I don't know, maybe 100 people an hour coming in. How many umbrellas do you expect? What's the chance then of seeing more than 5 people holding an umbrella on a rainy day at 10% rate? How would I find that out? So the idea here is, I'm not going to calculate it right now, but given this information, we can answer questions like this regarding up to 100 people just by knowing the probability of each person having the umbrella and how many people we're going to check. So that is a lot of information to have in advance. The real thing here for you to learn is the properties of these distributions, because we're going to use them for statistics in the practical sense. We don't get these statistics from just anywhere. What usually ends up happening is that we want to estimate those, right? We want to find out what P is, what's the chance of people holding umbrella on a rainy day, so that we can make predictions like this. So actually finding that value is very important to us. And so we're building this theory as a foundation for when we're going to remove knowing this and see from a sample what a sample can actually tell us about this probability. So right now we're just building that foundation to get to the probabilities, and then from here I can calculate probabilities. But what if I don't have that information? How could I get it? And this is the foundation on which we're going to rely. All right, so I say all this stuff, and then I give you an example here about the umbrellas. So we would write that X is distributed binomial with an n of 100 and a probability of 10%. And then I'm going to teach you how to use that information to compute the probability that X is greater than 5, for instance. There are other kinds of distributions that I'm not going to test them in the exam or anything, but it's up to you if you want to take some time to look at Poisson and hypergeometric distribution. They are quite popular. Poisson is used for estimating people in queues, lineups, having enough staff to receive, customer service calls, things like that. That's a Poisson distribution. Okay. Sorry, I had an interruption. So yeah, Poisson distribution is used for that purpose. Hypergeometric distribution is useful in a casino, where they try to figure out outcomes on cards. In fact, they have the same sort of parameters defined, like P and N, but they use them differently. In particular, hypergeometric is with selection without replacement. When we talk about sampling, when we talk about the binomial, each time the P is the same, right? That's a perfect example of with replacement. So each trial the chance of getting what we want, the P stays the same. So that's like, having a new deck every time. Your chance of getting a certain card or a diamond doesn't change from each. If you have a deck of cards, if you're selecting, the chance of getting a diamond wouldn't change if you use a new deck every time you select it. That would be with replacement. But hypergeometric takes care of the fact that you're taking and modifying the deck each time you take a card, and it allows for that. So there's there's particular uses of those distributions that are quite popular. So I'm not going to test you on them, but you should read about them just for fun. Just get familiar with different kinds of distributions. But I can only ask you for so much. So I give this example here for you just to be familiar with the binomial distribution, and when we get there, we're going to talk about. So we're going to talk about identifying you have a binomial distribution. So try this one. I'll give you a few minutes, and then we'll talk about it. Thank you, Yvette. You did it already. And let me give the others a few minutes. All right, how did it go? So this example I'm going to use, I'm going to refer to it later in the binomial unit. So it describes an experiment to identify if people have ESP. In this experiment, ESP is extrasensory perception. So in other words, can they read minds? So the experimenter looks at cards that are hidden from the subject. So I guess they put cards in front of themselves and the subject tries to read their mind. Each card contains star, circle, wavy line, or square symbol. The experimenter looks at each of the 100 cards in turn, and the subject tries to read the experimenter's mind and name the shape on each card. If a subject, so you got that part? If the subject gets at least 50 correct, they will have demonstrated that they have ESP. Let X be the number of correct guesses. In this case, X is binomially distributed with parameters N and P. What would the success be? The success, as Yvette outlined, will be correct guess. And a failure will be incorrect guess. Say you take the test and just guess all the way through. What is the probability P that you will correctly guess one card? So remember, there's 4 possibilities. And we're going to have to assume they're equally likely, because we didn't get any other information. So if there's 4 equally likely, then they all have to have probability 1 out of 4, so that in total 4 times 1 out of 4 is 1, right? So the P must be 1 out of 4. How many trials? Well, we're going to do this 100 times. And that's it. And then we're going to learn how to take this information. In this case, X is binomial 100 and 0.25. We're going to learn how to take this information and calculate things like, what's the chance that someone actually has ESP? So we're going to find what's the probability that someone correctly guesses at least 50 cards correctly. So X is the number of correct guesses, and I could even add out of 100. So we know what the chance is on 1. It's 25% each time. But we don't know what the chance out of 100 tries, how many are they going to get correctly? And what's the chance of getting a certain amount correct? All right. Any questions? That's binomials. Now, in terms of continuous distributions, I want to talk about the uniform distribution. We're going to, already learned about the normal continuous distribution, and then we're going to learn about the t-distribution. So right now I'm just going to teach you about the uniform. You already know about the normal, and I leave the t-distribution to later this week. So what is the uniform distribution? Before we go there, just a couple here. Like we talked about when I introduced the normal distribution, I used the variable height of women 18 and over. And I described that as a normal distribution, right? And we talked about, repeatedly, and I wrote it like that. We talked about X being distributed normal, 64-2. Another continuous distribution, like this density curve that's normal. The point being that it's continuous, right? And that there's no density at a point. We only calculate density or probabilities between values. Another type of continuous distribution is the uniform distribution. And here's my example. The number of hours a student studied on a certain date. They could have studied in the range of 0 to 16 hours. And let's say we believe that any of those are equally likely. So that creates a box here. This is a density curve, even though it's not curvy. But the principle is that the area here must be 1. So if the area here must be 1 and the possibilities are 0 to 16, and I say they're all equally likely, or any range of equal length is equally likely, what is the height? How does that affect the height of the distribution? I will need the height of the distribution to figure out questions like this. What's the chance of a person studying between 0 and 4 hours? Well, that's just a rectangle. In the rectangle, we know to get the area or density, or this represents like a relative frequency histogram or proportions under here or inside here. It's just height times width. The height, it turns out, is 1/16, and the width will be 1/4. Why is it 1/16? Well, because area must be 1. And the area is equal to height times width. The width is, and I use the notation, I refer to the high number as the upper limit and the lower number the lower limit, and I put them in numerical order. So to figure out the width in a continuous distribution, the width is going to be upper minus lower, right? The high one minus the low one. And then I multiply that by height. And this must equal 1. So what's the upper minus lower? Well, that's just going to be 16 times height must be 1. So that means that height has to be 1/16. So maybe I said more than I have to. Maybe that was useful. Okay, so that's how you figure out the height. Now this is obviously not to scale because I made this 16 and then I make this 1/16. So it's not to scale, but just to make a drawing for you. So that's 1/16. So now using that information, I can solve for any range of values. Probability of an event of individuals studying between 0 and 4 hours is just 25%. How did I get that? height, which I just calculated, times the width. Again, upper minus lower to find the width here. My pencil is disconnecting. All right. Keep in mind, if there's no density at a point, it would just be 0. So if I asked you, if x was defined like this, then something's wrong with my screen. Oh, I have no charge. One moment. Not sure why. Sorry. If I said probability of x, even if x was defined, so you always have to look at the definition. Look how I defined x now. Now it's defined as uniform 0, 16, lower and upper limit. That's all you need. These are the parameters. It seems simple, but those are the parameters that perfectly described the distribution and help me in that way estimate probabilities. So the probability x equals 4, 0, because it's a continuous distribution. Any questions about the rectangle? The uniform density? Okay, and so that's all I want to talk about now, because the normal distributions we already spent a lot of time, including the standard normal distribution. We'll talk about the t-distribution later. So the point of what we just discussed was to differentiate between discrete distributions and continuous type distributions. Make you see, when you see a density, you have to think to yourself, you see a distribution, you have to think, is that continuous, discrete? And that'll help you in interpreting what to do. Okay, so I have an exercise here for you. Did you try this already? So try this. Have a drink, get a snack, and I'll be back in 5 minutes. Well, we did cover an hour and a half, and there's no way I'm done probability yet. So I was ambitious with my plan to finish probability. All right, so let's see. Where are you guys at? What you need to do is draw a rectangle between -3 and 10. So we are talking about x is uniform, -3, 10. And we make a, let's use my thing here. And then so there's my uniform distribution. The question is, what is the probability that x is greater than 5? So I'm going to mark 0. And I'm going to mark 5. And then I'm going to mark greater than 5 so you can see this. So I want this. Now, x is defined a specific way. So even though this looks familiar, it's about the uniform distribution. So x greater than 5 I can write like that, or I could write x between 5 and 10 because it only goes to 10. Either of those is correct. Remembering, always put the smaller number first and then go from small to big in the signs. In this case, I want to use the width. The width is equal to upper minus lower. So this would be 5. And the height, so I'll just use h for height. What's the height? Well, the area must be 1 is equal to height times width. And height I don't know, but width I know because I use upper minus lower for the whole width. And that's 13. So this has to be 13. This has to be 13. So then height is equal to 1 over 13. So that's what it is. All right, so we're ready now. Questions? So you need to know the parameters. That will give you the number that you need. I mean, I'm not going to call it parameter, but I guess it is a result of parameters. The height will always be upper minus lower. So this is an important, I mean, I guess it's a parameter because I'm computing it from population values. So the h helps me once I know it. So I can calculate this probability. This is also height times width, but particular to this width. So it's going to be 513. And then the other question is about, oh, what happened? I didn't even realize that happened. Okay, sorry. Let me do that again. Everything got moved. It's because of this line thing. Okay, what I'm going to do is just draw on top of it and erase it if I can. I don't know if I can erase it. No. Okay, I'm not going to move over. That's all. Sorry. Okay, do that again. So this is 5, 13. Because height is 113 and width is 5, so those together make 513. And then less than 0, this is what I want. So the probability, you can either write x less than 0, or you can write probability -3 smaller than x smaller than 0. Those are the same thing. And the answer is, again, height times width, which is going to be, what's the width here? Width is upper minus lower, which is 0 minus -3 is 3. So this is height, which is 113, and width, which is 3. So that's the answer. So those are my answers. Questions? Moving forward. All right, so I wanted to do this problem. And then I wanted to talk about, I'll do that tomorrow. One thing I don't know how to do is how to delete this page. Well, okay, let me think about this. What I'm going to say is tomorrow what I'll do is I will go back and do this one. So I'll do this tomorrow, and I'll also do and I'll also talk again about this Bayes rule thing and where that number comes from. But right now I'm going to start to talk about the rules of mean and variances because I have enough time to cover it, and then we can be done with it. Oh, Valeria. Yeah, no, you can use decimals, Yvette, don't worry about that. I just like fractions because it doesn't look so messy, not cluttered. But people don't like fractions, I know. Okay, so I'm going back here. So why did I get 13? Look at how I did this. You see? This is important. So thanks for stopping me. So width is upper minus lower. Upper is 10. Lower is -3. So minus a negative makes +3. That's why I get 13. Is that okay? Thank you, Nivette. Right. The height is calculate for the whole rectangle because we need it. Right, and the individual width for each probability, exactly. And there are some examples, there are some other examples here that you can try for distributions, getting used to working with different shapes. So you should try those. So try that exercise, that practice assignment. and then we'll talk about them a little bit more tomorrow. But now I want to get through this, because if I can get through this, then we can totally finish binomial tomorrow in the first hour and a half, I think, or 2 hours, and then get into SDS. All right, so I have videos on a lot of this stuff. I think my video on this is really cursory, is the word. It means that I'm just reading through the notes, so it's not really animated. So hopefully I can improve upon that by talking about this now. So what we're going to do right now is talk about making distributions from already known distributions and how that affects those parameters, the mean and variance of the distribution. This is a really important technique. Oh, I mean, it's a rule, but it's a real important thing to know. And you'll see it everywhere. If you know, now that you're aware, as you become aware, you'll see it everywhere. It's all over units 5 and 6. So this is really important to cover. And you can read through these notes, and that's one stab at getting through this. What I want to do is simplify it as much as possible. So I'm just going to go to talk about this. If you get a distribution, and we did do this, right, where I give you a distribution, these are the possible outcomes, and these are the probabilities. In general, if this is a discrete distribution, right? I show you the different outcomes and their probabilities. So this is a discrete distribution. I should have written it somewhere in there, discrete. And so from here, I can calculate the mean as the weighted mean. The way it's been given to me, that's how I calculate the mean. And because this is a distribution, its mean is mu, the population mean. Okay? So we did see that already when I taught you about the standard deviation, and we talked about weighted mean in the GDS unit. So you've seen that before. And then I'll talk about this some more too tomorrow. All right, so what if I know about a variable x and let's say I know about a variable x, so I know its mean and variance. So I was able to calculate its mean and variance. I'm not going to speak about its shape. So this is what I'm going to do. I'm not going to talk about the shape. I'm just going to talk about x having this mean and this variance. What do we know? If we're to take that variable and we were to, okay, so I'm going to draw something. So this is, let's say we had a variable x. We'll just use the normal kind of shape, the symmetry. It shouldn't matter, but just makes it easier to visualize right now. So let's say this was our normal distribution, or whatever, a symmetric distribution with a mean of mu x and a standard deviation, sigma x. Let's say I wanted to, so this should look familiar to you. So let's say I wanted to center that distribution. Let's say I took mu x from every single value. So let's say I subtract, let's say the mean was, 64. And I subtracted every single value by 64 all the way around here, all along. What does that do to the mean of this new distribution, mu minus x? What would the new mean be? If I took every value here and I subtracted by 64. What would the new mean be? Nobody? Right. It'll be 0. So how did I get it? Whatever I do to every value, I also do to the mean. So if I subtract the distribution, in other words, every single value by 64, then I also subtract the mean by 64. Okay? So whatever I do to the mean, whatever I do to every value, I do to the mean. Whatever I do to the distribution, I do to the mean. So this shifts the whole thing over, and I have my new mean. So adding or subtracting, in fact, adds or subtracts to the mean. So we saw that before when I was talking about standardization. So that's just to give you an idea of something you've already seen. I'm trying to cling on to something you've already seen so it doesn't feel like you're learning something new. What happens when we, what would happen if we took this distribution and we multiplied every value by some value b? So, like 2 or something like that. What would happen to the distribution if I multiplied every value by a scalar? What would it look like? What would be the mean? Let's say it was 2. So I said 2x. What would it look like? So 64 would become 128. So whatever I do to every value, I also do to the mean, right? It becomes 128. And then 66 would become What would 66 become if I multiplied it by 2? Oh, you can't hear me? Let me see. Let me see what happened to my microphone. Can you hear me now? This new microphone that I got. Okay, this new microphone that I got, it just reset everything when I plugged it in. Oh, that's better now? Okay, so whatever happened, I had it turned down because I noticed the other settings, they were so loud. I made the microphone so loud before. Anyway, so multiplying by 2, what does this become? So what does it tell me that multiplying by a number bigger than 1 will cause the distribution to be more spread out? You see now 1 standard deviation. So the point is that the mean, first of all, it shifts over. This whole thing shifts way over. But it also becomes more spread out. It'll become more spread out as a result. So 1 standard deviation now ends up over here. So the mean, subtracting or adding will shift the distribution over, and it will also do whatever you did to the values you do to the mean. But multiplying every value by a number spreads out, or it squeezes together, right? If I divided by, remember when we did x minus mu divided by the standard deviation, if it was normal, this became much more peaked. I would show you like that. So this is the same as dividing or multiplying by a number less than 1. I'm just showing this as an example because we did this before, so this should be familiar. So this, when I divided by a number, it's like multiplying by 1 over. So this is a number smaller. Well, not necessarily if that was a fraction. But anyway, we did something like this before. Right? So what I'm saying here is, depending on what you multiply, you can either squeeze it together or spread it out more. So my point that I'm making is, if you shift the distribution, you shift the mean. If you multiply by a scalar, you expand, you spread I'll say change the spread of the distribution. That's all I want to say there. So if you shift the distribution, you shift the mean. If you multiply by a scalar, you're not affecting, well, you are affecting the mean. You're going to do that, it's going to affect the mean, because whatever you did to a value, you also do to the mean, but it changes the spread of the distribution. This doesn't change the spread of a distribution. I should add that. It does both. So what does this all mean? So this, what I've just described, if you followed, is the rules that are in the boxes here. So what I have here is, like I say, a distribution with a mean and standard deviation given. Now, if I take my distribution and I multiply it by something, and then I shift it, whatever I did to the distribution, I also do to the mean. This is what this says. So whatever I do to the distribution, I also do the mean, whether I'm shifting it or multiplying it by something. So why would you want to even do this? You're going to see, we use this a lot, but if you have lots of information on one variable, and it took you time to collect data and estimate that variable, and then you're considering alterations to it. Let's say you have gathered information, and you're going to see some of the exercises I give you. You've gathered information on incomes, for instance, and then you consider adjusting those incomes. You could multiply it by something to adjust for inflation, I guess, and then maybe, add a bonus amount. So these, you don't have to re-estimate income, or you don't have to wages, for instance. You use the one you have, and then you look at making the adjustments, and then that affects that. You don't have to re-estimate the whole distribution. You can use that information to find the mean for estimation purposes. Okay, so look what I did to the distribution, and then I just substitute x with the mean. So whatever I do to the distribution, I do to the mean. And then I proved this result using the discrete distribution, that concept that I described before. So I don't prove this for continuous distribution. So this is a discrete distribution. That's why I talked about discrete distributions before, but I don't prove this for continuous distribution because that involves calculus, and I'm not going to get into that. But you could just do this just as well. So you can take some time to step through this. This is not difficult. Notice whatever I do to the x, I do for every value of x, and I put it into the formula for the weighted mean. So x becomes a plus bx, and then redistributing all of this turns it into this. Oops. It turns it into this. And what does this mean? When you have a weighted, or you have a probability distribution with weights, the total sum of the weights will always be 1. So this sum becomes just a, because it's a times 1. And this one becomes the mean of x times b. So this is just the proof. You can sit and look at it. You just have to go in between these two to see what they did. And if you remember what I just said and some of the illustrations I made, whatever I do to the distribution, I also do to the mean. Remember that. Now, I give you some examples, and then I talk about the sum and differences of means. And here's another box. So what if I have two distributions that I know about? I know about a random variable x, and I know about a random variable y. So let's say I have information on returns to a certain stock that's available in the market, and I have information on a second stock, and I'm thinking about purchasing both of those and their joint probability distribution. Now, I don't have to go and collect information on holding both of them. I can use information about each of them and these rules to estimate what I can expect as my return of holding both of them. So as long as I know about x and as long as I know about y, I know about having them both in a portfolio together. So the rule is the expected value of the sum of variables is the sum of their expected values. I mean, it has a ring to it, no? Again, I could prove this in a simple way with the discrete distribution. And I think I do provide it below. So to have a read through that, it shouldn't be intimidating. Oh, maybe I didn't prove it. But you could prove it in the same sort of way. You just would take this approach and expand and recollect your terms to come up with the result. It's tedious, but you can do it if you had to. Okay, so the expected value of the sum of variables is the sum of their expected values. And that would apply here too, where you can see this as this is a difference of the expected value. Well, anyway, this is the expected value of the difference of two variables, and that would also be true for the difference of the expected values. And I leave some examples for you to read about. So if you trust me on those, now let's go into the variances. What do we know about the variances? So here's the formula for discrete distribution and variance, and we did do this back in GDS. I made a video. It's my most popular video. It went viral. I don't know why. Oops. I don't know why that happened. It hit the Asian market. So you can review that if you want. So this is the variance. So it is the weighted standard deviation. This is actually the variance, the weighted variance. Now this is another way, I never wrote it this way before. This is another way of expressing it. Remember that it is the average, right? It's the average of the squared deviations from the mean. That's what it is. And when you have it as a distribution, that's what it would appear like. So what is this? So this is the formula for the variance that you've seen before. And what I describe is the fact is you can also write it like this. The variance of x, the symbol, can also be expressed like this. And I don't prove that, but that's another expression. Oh no, I do prove it. I prove it here. Again, it's expanding your terms from above. So square this is a perfect square. Well, anyway, you distribute this through and you get this result. And then notice, following the rules of means, the expected value of, this is x squared, so this is x times x. This is 2x mu plus mu squared. So if you imagine, this is just a scalar, right? And this is still a variable in it. So this reduces, this just becomes, so remember the rule that the expected value of a sum of variables is the sum of the expected values. You're going to use that rule, and the difference of expected values comes from the difference of variables. So the rules that we already discussed are being applied here. So this is a good application of the rules, and it reduces to this. So this is actually just, practice. You don't have to apply this ever. Just practicing the rules. All right, so what do we know? So what I told you before, we refer to this, I refer to this, I didn't say it before, as a linear transformation. When you, it looks like a line, a plus bx, right? But the point is that you're multiplying by something and then adding a shift. So we're going to do this now to see what happens to the variance. And now going back to our discussion, what happens to the variance? What did we determine? When you multiply a random variable by a scalar, it can either expand the variance or contract the variance depending on the value. But notice shifting doesn't change the spread of the distribution. So if it's just talking about variances, shifting doesn't affect the variance, okay? So what happens here, if I want to know the variance of this new distribution, it's going to be, it's only going to be affected by the shift term. It's not going to be affected by the A. So this just leaves, this actually reduces to variance bx, and remembering this letter, now you can do this with the formula that you have above. You can put a b in there and see what happens. But I'll tell you right now, that b, anything that goes into the variance, actually I'll show you. Maybe it'll help. Anything that comes out of they call this, we refer to this as an operator, like a variance operator. And it goes through and it kicks out the A. The A has no significance. Shifting doesn't affect the variance, but multiplying by something does. It could spread or contract, so we care about that. Now, what does it actually do to the variance? Well, it just becomes a square term. Now, let me see if in a less complicated way, I could show you that. I just know the Greek letters can be intimidating, and I lose attention. So what I'm going to say is, let's say we were doing this just for the sample. So for the sample standard deviation for x, it would be like this, right? Now imagine if we put a number in front. And I'll just say bx because it could be any number. How is that going to affect things? No, I don't want to do that. Not in front of there. I want to put the b in front of the x. We define a new variable y as bx. So what does that accomplish? So if every value has a b in front of it, bxi minus bx, I did this backwards. Sorry. This is xi, x bar. So if I do that, are you with me still? I'm making a lot of mistakes today. I'm not feeling great. All right, so if I put a b in front of each x, look what happens to the b. What happens to the b? What happens to the b? Yes, you see it? So basically I could do this. I could pull it out, couldn't I? So anything that goes in here, notice it gets squared. And that's the important point. All right, so the variance operator, the standard deviation, oh, and I didn't even put the square root around. I'm going to write, let me tell you, this is not standard deviation, this is variance. Right? Everybody okay with that? With me putting a square there? So this is variance. This is a sample variance. So I got to correct myself. All right, so let's recap. So this is the sample variance formula. I'm not taking the square root. I'm leaving it like this. So I say, what if we invent a new variable called bx? So then every x will be pre-multiplied by b. But then I can take the b out. So in fact, what it means about the standard, or sorry, the variance is that the variance is actually b squared times the variance of x. And this is the variance of y. Everybody with me? So I like to show that because you work more with the sample standard deviation. Maybe it's easier to visualize, but it's the same exact thing, except I have a mu there and an n there, or no, a pi. So So just to avoid confusion. So did you follow that? So whatever I did to the x, I do to every value. When I multiply the random variable by b, I do it to every value. And so that comes out as a b squared. So essentially, this is just sx squared times b squared is really sy squared. Is that okay? And we don't care about the a because adding a value to every single value in a distribution doesn't change the variance. It definitely changes the mean, but it doesn't change the variance. Is that okay? Do you understand this box? No? No comment. Guys make me laugh. All right, so we'll come back to this. So the variance of a linear transformation, if I was to add and multiply, or multiply x by a value and then add a shift, the variance would just be changed by the scalar. Now, I like to write it as variance and teach it as variance, but you need to realize it's very simple if you just look at the standard deviation. This just simplifies. I could just write the standard deviation is b sigma x. Tell me somebody gets it. So I've just taken the square root of both sides to get that. So whatever examples you can use to understand this, the better. Nope. Okay. Well, I need to proceed. So what about, so we're almost done here. There's not much more. What about if I take variables and I add them together, or I take variables and I subtract them from each other? What does it do to the variance of those variables, of that new variable, of the sum or the difference? Well, like the expected value, the variance of a sum or difference of variables, of random variables, is the sum or difference of their variances. So you guys are going to be okay with this? Only if what? So this is a nice simple result that the variance of a sum of variables is the sum of the variance. What happened here? First of all, we're going to look at this. How is this the same? Can someone explain that? I'm going to explain that. So the operator x minus y, when it goes in, it makes a sum, right? Let me rewrite this as a sum. I made it a sum. And then I'm going to use the first rule. I need more space. So you see what I'm getting at? You see what I'm going to do here? You see my trick? And why this is the case? Anybody? What am I going to do? What am I going to do, Nivette? What am I going to do? What's my trick? So what I'm going to do is that's a long way of writing it. I square, like this is a -1. This is like the b, and it gets squared, remember? So this is variance of x. This is variance of y with b squared in front. So that's why that just becomes y squared. So in other words, even if you're subtracting variables from each other, the variance and the variability of this new variable, it's a contribution of both variances. It's the sum of the variances of the individuals random variables. So this is all right, but this is only true when the variables are independent, when there's no correlation between them. That's the only time this is true. If there's correlation, we have a longer formula. If there's correlation, we have a longer formula. And I'm going to describe where that formula comes from, and then we're going to go. And you're going to have time to just relax, think about this. So I've tried to summarize all this. There's a lot of pages here, and you need to know this for the end of the term. I give you I give you several examples. Most of them have answers at the end. So only one has no answers. So try this for tomorrow. We'll talk about it. Maybe I should make it bigger. You guys can't see it. All right, so I am going to figure out what's the variance of the sum of these two variables. This is a scalar multiple of x, right? So it's like, scalar multiple of x. This is a scalar multiple of y, and I'm going to sum this. So what is the variance of this new variable that I create? It's okay, Nivette. Don't worry, I understand. You're going to be okay when you do that, when you rewatch. So we want to create the new variable, and these are the contributions we're going to consider. How does what is the variability contributed by A? So it's like the covariance of AX, not A, but AX with AX. This is actually, if you think about it, and again, I'm going to use the sample formulas to motivate your thinking, I hope. So what is this? This is that's the covariance. Simple. This is the sample covariance formula. And what is that? Are you guys following? So what is this? What did I just do? I just confused you. Hold on. Let me erase this one and rewrite that. So this is this. And then if I factor out the A's, I get A for the first one, A for the second one, like that, right? So that's basically, so these are just scalars, these are just numbers. Like this is just 1 or 2 or 5 or 15 or 0.006. Okay, and I can pull it in front. So now what is this? Tell me what this is. What is this? Isn't that variance of x? And this is just a squared. So this is going to be a squared stare at that a bit, because then I'm going to ask you what this one is. Basically, it's a pattern. You're going to see the pattern. So what I've said is I want the relative contribution of the variables to calculate the variance. So we begin by thinking how A what is the spread contributed? What's the variability contributed by x? So we do covariance of ax with ax, and that gives us this. What is this one? by with by. What would you get? No one? No one sure? You would get, you would get the same thing, b squared sigma y squared, because this is really, when it's a covariance, yes, very good, Nived, with the y. So you would get covariance of a variable with itself is just the variance, and then this term comes out as a square. So that's done. So we're good with those. Now what about these terms? What do you think this one would be? Actually, before I even ask that, is this not the same as this? Because it doesn't matter if if you write ax by or by ax, they give the same answer, right? It doesn't matter which one you make x and which one you make y when you calculate the covariance or the correlation. We talked about that. So this works out to be so with the same logic, I can do what I did above. I could write 1 over n minus 1, and then I have ax minus ax bar, by, I have someone sawing behind me. Hope you don't hear that. By minus by bar. So that's why you get this result. Because the a and the b will both factor out, and it will leave this. This means covariance. This is the symbol for covariance. Yeah, I was muting because I don't want you to hear the saw behind me. Okay? Everybody okay with that? Because I can factor that out. Okay, then I can pull the a and the b out and leave the covariance. Okay, so then this is the same. So in summary, variance of ax plus by is equal to variance of x plus variance of y with the b squared, and x had the a square, plus 2 covariances of xy, but I can use that symbol, to AB sigma xy. So I can write it like that, or I can write it with covariance, either one of those. All right, so what if I'll just make it plus for now. So what would that be? Use the same pattern. What will you get? So we can make another chart, but you should get the hang of this. If you haven't already, you should see if I put AX, BY, CZ, AX, BY, CZ, this is going to become A squared sigma X squared. This one's going to become B squared sigma Y squared. And this one will be C squared sigma Z squared. And then okay, so what about the other things? So notice it's a 2 by 2, so every pair is doubled. Okay? It's going to be, here's going to be AB, I'll put it in alphabetical order, sigma xy. And this one will be AB sigma xy. So there's two of them. And what about Z? This one will be AC sigma xz, and this one will be AC sigma xz, two of them. So it's just going to be pairs of two, not a three. Okay, that's the most important thing to realize here. So this is going to be in alphabetical order, BC sigma YZ, and here's going to be BC sigma YZ, and there's two of them. So the formula is going to be this, and then 2, 2, and 2 with all the pairs. So the variable created, the variance of the variable created from for x, y, and z is going to be
a squared sigma x squared plus b squared sigma y squared plus c squared sigma z squared, and then the pairs 2 a b sigma xy, 2 b c sigma yz, and 2, these are 2's, not to be confused with z's, AC sigma x z. So you guys, you must, if you got that the second time, good for you. It's just a pattern. The principle is that multiplying a variable by a scalar affects the variance. That's the main underscore thing here. And can you guys see that? And that's it. So this approach, this technique that I've demonstrated is basically what is in the box here. These are the results, and this is in the box here. I didn't use the symbol sigma xy, but I'll make a note. So what I just showed you about making like that matrix is this box here. This just says make the matrix of however many variables you want to covary, make the matrix. So I'm finished touching this material, but I will go and fill in just a few things that I left out tomorrow, and then we'll get into binomial. All right, so review, and you'll feel better about this stuff. There, like I say, okay, there's these exercises here. So try this for Tuesday. Have a look at the others. Just step through them to prepare. So the test will be on this new probability stuff, the binomial and sampling distribution of a sample statistics, Unit 5, and a little bit of Unit 6 on the test. But the final exam will have more Unit 6 on it. Okay? Any questions? I mean, I should commend you that you've stuck with it and you guys are doing well and dedicating yourself and destroying your weekend to do the test. But it's almost done. Just a few more days. Okay, good night. Have a good rest and keep me posted. I have to see, some students wrote me questions. I have to check what they were and address them tomorrow. Buenas noches. Sorry for the gaffes today, mistakes. I think I fixed them all on the way. Take care.